An important topic in linear algebra is how you can use a set of vectors and take a linear combination of them and get zero. That topic is called linear independence. So to see why this is important, let's look at a couple examples. So recall that we can get any point in R2 real 2 space by taking linear combinations of, say, 1, 0, 0, 1. Or 1, 0 and 1, 1. Or say 1, 1 and 0, 1. Or we could take all three of these vectors here, 1, 0, 1, 1, 0, 1. And there's something about our third choice that's not as good as the first, sorry, our fourth choice that's not as good as the first three choices. And one reason is the set is not as small as possible. These are all sets of 2 vectors that we can use to get everything in the real plane. This is a set of 3 vectors, so it's not as small as it could be. And another problem with it is that there's more than one way to get each point using these 3 vectors. So for example, if we look at the point 2, 1, we can get there by going, let's see, 2, 1 equals, well, obviously 2 times 1, 0 plus 1 times 0, 1. 2 over 1 up. It also equals, we could go up to 1, 1 and then over 1. So it equals 1 times 1, 1 plus 1 times 1, 0. And we could also go down 1 step first if we wanted, and then take 2 steps in this direction. So it could be minus 0, 1 plus 2 times 1, 1. So we've got 3 different ways to get to the point 2, 1 using these 3 vectors. So these are 3 different linear combinations. That give the point 2, 1. And there's a lot of advantages to using a spanning set which is as small as possible. So the name for what's good about these first 3 is called linear independence, and the name for what's bad about the fourth one is linear dependence. The first three are linearly independent. The fourth is linearly dependent. Let me give definitions of those terms. We call a set V1 through Vk of vectors linearly independent if the only linear combination of them that gives 0 is the zero linear combination. So if that's the only way to get 0. And we call them linearly dependent if there is another, let's say if there is a linear combination, a non-zero linear combination, so C1 V1 plus dot 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 CK VK equal to 0. So by non-zero linear combination, I mean not all of the C's are 0. It's better if the only linear combination that gives 0 is the zero linear combination, because that makes it easier to recognize the 0 element of the vector space. This makes it easier. Oops, running out of space. This makes it easier to recognize the 0 vector in computations. It's a fact that a set V1 through Vk, I'm thinking of k as a number which is at least 2, is linearly dependent if and only if some vector Vi equals a linear combination of the others. and which vector vi is usually not unique. So if you can express vi as a linear combination of the others, you can probably express a different vector in the set as a linear combination of the others as well. So to see why that's true, since this fact says if and only if, I have two implications to show. So suppose we have the set that's linearly dependent, and we'll show that each vector vi equals a linear some vector vi equals a linear combination of the others. And then for the other direction of this, we'll say suppose we have a vector which equals a linear combination of the others, therefore we must have something that's linearly dependent. So for one direction, suppose v1 through vk is linearly dependent. Then there exist, this backwards e means there exist coefficients c1 through ck not all zero, such that c1 v1 plus dot 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 ck vk equals 0. Now if they're not all 0, let's pick one of them that's not 0. So suppose ci is not 0. Then we can write, we take that one that's not 0, keep it over here and subtract everything else. Then we can write ci vi equals negative c1 v1 dot 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 negative ci minus 1 vi minus 1 negative ci plus 1 vi plus 1 dot 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 negative ck vk. And then if we divide by ci, we've got vi. We can divide by ci because it's not 0. We chose one that was not 0. So then vi equals negative c1 over ci v1 negative ci minus 1 over ci vi minus 1 negative ci plus 1 over ci vi plus 1, etc. negative ck over ci vk. So there we have it, one element expressed as a linear combination of the others. For the other direction, let's suppose some vector equals a linear combination of the others. So let's suppose, I'll use a different letter here so we don't confuse it with the first part of the proof. Suppose vj equals something like d1 v1 summed up to di minus 1 vi minus 1 di plus 1 vi plus 1 dk vk. So vj equals some linear combination of the others. And let's make these j's. So vj is a linear combination of the other things, everything except for vj over here. Then we can subtract vj from both sides. To get 0 equals d1 v1, etc. up to gj minus 1 vj minus 1 minus vj plus dj plus 1 vj plus 1, etc. up to dk vk. So now we've got 0 equal to a linear combination. And how do we know these coefficients are not all 0? Well, we know that because the coefficient of Vj is -1. So even if all the d's are 0, we've got at least one coefficient there that's non-zero. So that completes the proof of this fact. All right, so now to put this idea into practice, let's look at 4 polynomials and decide whether the set of 4 polynomials is linearly dependent or independent. So let's decide if the set of polynomials (1 minus 4x cubed) (2 plus 2x) 1 minus x squared plus 2x cubed, and 2x minus x cubed. Is linearly independent or dependent. Minus 4x cubed plus c2 times 2 plus 2x plus c3 times 1 minus x squared plus 2x cubed plus c4 2x minus x cubed. Is that being equal to 0 possible? Without all of the coefficients being 0 themselves? Of course it's possible if all the coefficients are equal to 0 themselves. It's only interesting if there's a way to put these 4 polynomials together with coefficients that are non-zero. So if the only way this is possible is to have all the coefficients equal to 0, then we've got a linearly independent set. If there's some other way to put them together to get 0, with the coefficients not all 0, then we've got a dependent set. So we'll try to solve this. Let me call this equation star here. And 0, when we have an equation in polynomials, we can rewrite 0 as 0 plus 0x plus 0x squared plus 0x cubed. And then we'll compare coefficients of the same powers of x on each side. So this is going to be a linear system of equations, and the c's are going to be our variables. So let me give myself a little bit more room here. Because we have to think about what the equations are. We're going to break this equation into a couple of linear equations. So if we look at constant terms on both sides, that's the 0 on the right-hand side without any x's, and then the constant term of c1 times 1, etc. on the left-hand side. So we have 1 times c1 plus 2 times c2 plus 1 times c3 plus 0 c4, because there's no constant term here. So that should be equal to 0. And then we look at coefficient of x. So there's no coefficient of x next to the c1. There's 2x c2. So 2 is the coefficient of c2 times x. no coefficient of x there, 2x c4. So 2 c4 times x equals 0x on the right hand side. And then if we look at the coefficients of x squared, we've got nothing c1, nothing c2, minus c3, so minus 1 c3, and then nothing c4. And then coefficients of x cubed, we've got minus 4 c1, nothing c2, plus 2 c3, x cubed, and minus c4, minus 1 c4 x cubed equals 0 x cubed. All right, now this system of equations is definitely going to have a unique solution. It certainly has a solution c1, c2, c3, c4, all of them equal to 0. So the question is that the only solution? Now this system of equations will have a unique solution if this determinant is non-zero, because if it's non-zero we can invert it and then say c1, c2, c3, c4 equals this inverse times 0. Let's call this matrix A. Then c1, c2, c3, c4